Bismillahirrahmanirrahim. My respected students, Assalamu alaikum wa rahmatullah. I am going to discuss about pharmacodynamics. Pharmacodynamics is the branch of pharmacology that deals with action of drugs along with its mechanism. Means it deals with the dynamicity of the drugs. For example, paracetamol, it produces antipyretic effect, it produces analgesic effect. This analgesic effect, how does it occur? These antipyretic effects, how does it occur? So these components are pharmacodynamic component. That means it deals with the dynamicity of the drugs, means action of drug along with its mechanism. Now, drugs can produce their effect usually by two means. One, by binding with some specific component of the cells, or by selectively binds with some components of the cells. So that is known as specific or selective, or also known as receptor mechanism. There are few drugs which do not bind with the specific component of the cell. Mere presence of the drug will produce some effect. So they are not selective, they are non-specific, that is non-receptor mechanism. So drug may act by specific or receptor mechanism, or by non-specific or non-receptor mechanism. Now what is a receptor? Receptors are macromolecular structures, protein or lipoprotein in nature, situated on the cell membrane or within the cell, with which drugs combine mostly reversibly and form drug receptor complex that initiates a series of events leading to the characteristic effect of that drug. Once again, receptors are macromolecular structures, protein or lipoprotein in nature, situated on the cell membrane or within the cell, with which drugs combine mostly reversibly and form drug receptor complex that initiates a batteries of events leading to the characteristic effect of that drug. These receptors may be physiological, may be silent receptors. Physiological receptors are functional as well as spare receptors. They mostly physiological functional receptors come into play, and spare receptors come in emergency situation. Their role is to produce effect of the drug. There is another group of receptor which binds with the drug but will not produce effect. They are not known as silent receptors. For example, plasma protein, they bind with the drug but will not produce any effect. In plasma, drug remains in free form and binding form. Binding form is inactive form. When free form reduces, then drug from the binding form will be released. And this free form will be produce effect. But it is the binding form that will not produce any effect. It will act as a storehouse or reservoir or go down. That's as there is no effect, but it binds with the drug, so it is known as silent receptors. An example is plasma protein. Now the receptors mostly situated on the cell membrane. Most of the receptors are located on the cell membrane, and they are categorized as type 1, type 2, type 3, and also on the cytoplasmic and nucleus. In cytoplasmic nucleus is steroid receptor, and in nucleus receptor is thyroxine receptor. Now receptors may be, so the composite classification of receptors may be type 1, type 2, type 3, type 4. And type 1 membrane, type 1 on the membrane, type 1 on the membrane, and type 3 is cytoplasmic as well as nuclear receptor location. This is the location of the receptor. Now in case of type 1, the receptors may be ion channels, may be enzyme, may be carriers. maybe ion channels, maybe enzyme, maybe carriers. Maybe ion channel receptors. These are sodium channel, potassium channel, chloride channel, calcium channel. With this drug, with these receptors, drug binds and form complex. This complex causes there is alternate exchange of the ions leading to either hyperpolarization or either depolarization or hyperpolarization. When there is depolarization, there will be spike potential, there will be muscular contraction in case of skeletal muscle, contraction of heart in case of cardiac muscle, there will be neuronal firing in case of nerve, there will be glandular secretion in case of gland. These are due to depolarization. But when there is hyperpolarization, then heart will relaxation, muscle relaxation, neuronal firing stop or inhibition, and no glandular secretion. And these effects occurs in within millisecond. And the example is nicotinic receptor of acetylcholine. Then in type 2 receptor, they are involved with drug interacts with the enzymes, drug enzyme complex form, and this complex is divided into two sides. One wing that behaves like type 1, that is through ion channels they will produce their effect either by depolarization or by hyperpolarization. And the main bulk of this complex ultimately causes involvement of second messenger system. Second messengers are cyclic AMP, cyclic GMP, IP3, inositol triphosphate, DAG, diacylglycerol, then calcium. These second messenger systems involvement occurs, then ultimately it causes protein kinase involvement and ultimately phosphorylation and dephosphorylation. Finally, drug will produce effect. Example is adrenergic receptors produce effect in this way. Now, enzymes, the tyrosine kinase, it is also known as insulin receptor. Here, the insulin, this receptor, it has got two subunit. Alpha subunit remains outside the membrane, and beta subunit remain on the membrane. Now, insulin, which binds with the outer membrane, then it forms complex with the alpha subunit, then it is called as internalization and signaling, and ultimately leads to autophosphorylation. As a result of autophosphorylation, there is increased formation of sub-enzymes and decreased formation of other enzymes. Insulin increases glycolysis and increases glycogenesis. And the rate limiting step in glycolytic pathway is glucokinase, phosphofructokinase, pyruvate kinase, and glycogenesis pathway is glycogen synthase or synthetase. And this enzyme production is increased. On the other hand, in neoglucogenesis and glycogenolysis, there are rate limiting enzymes or steps. They are glucose 6-phosphatase, fructose 1,6-bisphosphatase, then phosphoenol pyruvate carboxykinase and pyruvate carboxylase. These enzymes are inhibited. So, by stimulating glycolytic pathway and glycogenesis pathway and inhibiting neoglucogenetic pathway and glycogenetic pathway, insulin decreases blood sugar level. Now, in type 4, the examples are steroid and thyroxine. These drugs enters, they are highly lipid soluble drugs. They enter the cytoplasm, they cross biological membrane, and steroid binds with its receptor, form complex in cytoplasm, then that complex enter into the nucleus. Or thyroxine, by crossing membrane, they enter into the nucleus and form complex with the nucleus, and there is gene transcription then translation, then transcription, and finally protein synthesis, and it will produce then effect, growth and multiplication. So in type 1 receptor, action occurs within millisecond. In type 2 receptor, action occurs within second. And in type 3, action occurs within minutes to hours. And in type 4, hours to days, it will take time to produce effect. So drug interacts with the receptor and form drug receptor complex. That complex mostly reversibly and initiates a series of events leading to the characteristic effect of that drug. Now, a drug binds with the receptor and can produce effect. This is known as agonist. A drug binds with the receptor cannot produce effect. That is known as antagonist. Agonists have two qualities. One is binding capacity, that is potency, and another one is action producing capability, that is intrinsic activity. And drug having only affinity but no action producing capability, that is no intrinsic activity, they are known as antagonists. There is another group which has got affinity and has got efficacy of weak efficacy when used alone. They are known as partial agonists. So antagonist cannot produce effect, but it can antagonize the activity of the agonist. And partial agonist, when used alone, behaves like weak agonist, but when used in presence of a strong agonist, it behaves like antagonist. Example of agonist, antagonist, and partial agonist are adrenergic receptors is classified as alpha receptor and beta receptor. Alpha agonist is methoxamine, beta agonist is salbutamol, and both alpha and beta agonist is adrenaline. On the other hand, alpha antagonist is prazosin, and beta antagonist is propranolol, and alpha beta antagonist is levetiracetam. On the other hand, cholinergic receptors may be classified as muscarinic receptor and nicotinic receptor. Agonist of muscarinic receptor is muscarine, and agonist of nicotinic receptor is nicotine. And both acetylcholine is an agonist of both the sides. And muscarinic antagonist is atropine, and nicotine antagonist is atacurium, and nicotine antagonist is atacurium. Now, partial agonist example is nalorphine, oxprinolol, pindolol. So these are the agonist, antagonist, and partial agonist. Now drug binds with receptor and form complex, produce response. This is dose response. Dose response may be of two types. One is graded dose response, and the other is quantal response. Graded dose response means with the increase of dose, there will be increase of response up to a certain limit, or with the decrease of dose, decrease of response up to a certain limit. For example, CNS depressant drug, hypnotics, when used in lower dose, it will produce anxiolytic activity. A bit higher dose will produce hypnotic activity. A bit higher dose will produce anti-epileptic or anticonvulsant activity. A bit higher dose will produce anesthesia. A bit higher dose will produce coma. A bit higher dose will lead to death of the patient. Before death, all are reversible, and death is irreversible. And when these drugs ultimately metabolized, concentration decreases, and then from coma it goes to consciousness. From coma it comes to hypnosis, then goes below anxiolytic effect, and finally regains consciousness. So this is a graded fashion with the increase of dose, increase of response. This is graded dose response. Other example is blood pressure elevation or increase or decrease of blood pressure, muscle contraction or relaxation, blood sugar level increased or decreased. These are examples of graded dose response. Now, quantal response, it follows or learn law. When there will be action, it will be in full. When there will be no action, it will be also in full. And the example is lethal dose, the amount of drug that will produce lethal effect. Either it will produce lethal effect or it will produce no lethal effect. So, or another is it may produce convulsion, it may not produce convulsion, it may control convulsion, it may not control convulsion at all, or it may produce arrhythmia, control arrhythmia, or it may not produce not control arrhythmia, or it can produce arrhythmia or control arrhythmia, or it cannot produce arrhythmia or it cannot control arrhythmia. These are the examples of quantal dose response. These responses can be graphically represented, and both the response curve will indicate their affinity or potency as well as selectivity. But great dose response will indicate intrinsic activity, and quantal dose response indicates variability. Now, variations in response. Response, when drug is given, it will produce response. That response may vary. Vary means variation may be quantitative variation, may be qualitative variation. This in quantitative variation, first I discuss about quantitative variation. In this variation, action may be increased or action may be decreased. Now, first is action may be increased, and action may be increased. This is known as hypersusceptibility or supersensitivity, that is up-regulation of the receptor. Example is thyrotoxic patient, they are unusually sensitive to adrenaline. Similarly, patient of subclinical glaucoma, they are unusually sensitive to aspirin, or patient of subclinical bronchial asthma, they are unusually sensitive to methacholine. There is increased activity receptor, increased super sensitive to the receptor, and produce exaggerated activity. Now, others, when two drugs are used together, then their combined effect is the product of their sum. As for example, antacid, aluminum hydroxide, and magnesium trisilicate given together. In this situation, the sum of their effect will be 1 + 1 = 2. On the other hand, there may be paracetamol with caffeine or ergot with caffeine. Their activity is equal to their sum of their products. And there is another situation in which one drug will increase the activity of the another. And in that situation, we can call potentiation or synergism. And the model or best example of this is cotrimoxazole, which contains two drugs. One is sulfamethoxazole and is trimethoprim. When these two drugs are combined together, they individually each drug is bacteriostatic and narrow spectrum. When combined together, they become bactericidal and broad spectrum. Individually, resistance develop against individual drug quickly, but when combined together, resistance develop chance of developing resistance is very less. And individually, when drugs are used, their amount is more, and when combined together, their amount is 10 times less. So 10 times less amount, thereby toxic effects will be less. So this combination, this increased activity is known as chemotherapeutic potentiation. In this way, action of the drug can be increased. On the other hand, action of the drug, variations of drug action may be decreased, and this decrease is due to down regulation of the receptor. And here maybe tachyphylaxis. Example are tachyphylaxis and tolerance, dependence, and addiction. Here there is down regulation of the receptor. And another one is antagonism. Antagonism means is a process by which one drug will inhibit the activity of another. This antagonism may be of several types. Maybe physical antagonism, as for example heat and cold. Maybe chemical antagonism, as for example antacid and hydrochloric acid. Maybe pharmacological antagonism, maybe physiological antagonism. Physiological antagonism example is acetylcholine and adrenaline, histamine and adrenaline, then insulin and glucagon. They are physiological antagonism. Here, both drugs will act on different receptor, both the system is same, but the receptors are different, and they are effect is antagonistic, and both the drugs are agonist. And there is another antagonism is pharmacological antagonism. Here, both the drug will act on the same receptor. One is agonist, one is antagonist. As for example, cholinergic drugs and anticholinergic drugs, adrenergic drugs and anti-adrenergic drugs, histaminergic drugs and antihistaminergic drugs. So these are the antagonists. So in this way, there are quantitative variation by which one drug increase or drug action may be decreased. Now, there is one thing is important here. In this way, drug response may undergo variation. Now, we have discussed about variations in response. This variation may be immunological and may be pharmacogenetic variation. Immunological, these are qualitative variation. Previous one is quantitative variation, and now I am discussing about qualitative variation. And this qualitative variation is immunological or allergic origin or due to hypersensitivity reaction. Here antigen antibody is involved. Here first we give an antigen, the drug that behaves as a peptide or antigen that will produce antibody which attack on the mast cell, and subsequent when the same drug is repeated, then the antibody recognizes the drug as antigen and it forms complex with antibody, and then antigen antibody complex formation occurs, their inflammatory complement and mast cell ruptures, from which there is release of histamine and bradykinin. This histamine causes bronchoconstriction and causes dilation of the peripheral blood vessels, decreased peripheral resistance, and oozing of blood from the vascular tree. Ultimately, there causes cardiorespiratory arrest and patient die unless managed properly. This situation can be managed by given adrenaline, and adrenaline will produce a double-barreled action and produces bronchodilation and causes vasoconstriction and resuscitates heart. Thus counter the situation. And the allergic reaction is mediated by H1 receptor, so H1 blockers can be given, supported by and also by glucocorticoids can be given. So this is allergic reaction. This may be categorized as type 1, type 2, type 3, type 4, and it may be mild, it may be moderate, it may be severe. Severe and immediate fulminating type reaction is called type 1 reaction, that is known as anaphylaxis. And the example, penicillin G can produce anaphylactic reaction. So this is immunological reaction. It is a qualitative variation in the response. Also, there is another example is pharmacogenetic response. Here, genetic factors responsible for it. For example, primaquine, an antimalarial drug, when given to a malarial patient, it will cure malaria. But when it is given to a black, 1 in 10 black, who has got deficiency of glucose 6-phosphate dehydrogenase enzyme, he or she may develop hemolytic anemia while giving primaquine therapy. What is the reason behind is that patient may have atypical or abnormal glucose 6-phosphate dehydrogenase enzyme. This enzyme is responsible for production of NADPH. This NADPH acts as a cofactor for the activity of glutathione reductase enzyme. This glutathione reductase enzyme converts oxyhemoglobin to reduced hemoglobin, which is the active and operative form of RBC. When primaquine, or not only primaquine, other drugs which possess oxidizing capacity, more oxidizing capacity, they will produce more oxidized hemoglobin, and that hemoglobin